Hi, good morning, everybody. Today we're going to be looking at chapter 19 in the first 4 sections or so. We're going to be focusing on chemical thermodynamics in this chapter. Some concepts we've heard before, some concepts we haven't. Some of these were very briefly discussed last year in your honors chemistry class. Some of them have been briefly discussed over the course of this entire semester, like when we're talking calorimetry and things of that nature. So let's get started. So when we talk about thermodynamics, we want to kind of immediately draw to mind the idea of heat. And we spent a little bit of time doing this back in chapter 5. And we introduced this idea of the conservation of energy, where we cannot just create it from nothing and we can't just destroy it into oblivion. Those things don't happen. So one of the things that we want to take from this, in this chapter, we're going to start thinking on a universe scale, which just means everything you can think of, all rolled into one. So if we think about the amount of energy available in terms of food, or in terms of the sun, or in terms of stars, all of that is going to be constant. Put it all together, it will not change from day to day. That being said, energy can be converted. We know this because when we eat, we convert our food into our usable mechanical energy. So just kind of keep in mind that we're thinking on a grander scale in this chapter. So that being said, we're going to talk a little bit about this idea of a spontaneous process. So what this means is just that this will happen without any kind of input from us. So if I put two things together and I want an explosion to occur, then all I have to do is put those two things together. I don't have to heat it. I don't have to monitor it. I don't have to add anything else. If I put those two things together and they produce an explosion, that's a spontaneous reaction. Or if I put those two things together and they produce a liquid, that's a spontaneous reaction. If some reaction occurs and the things change, the substance changes from one substance to another, then that is considered a spontaneous reaction if and only if we did not put anything in to make it happen. Okay, and the example here involves these two gases, and in between the two gases there's this barrier, and that barrier, once it's removed, allows the two gases to mix, and when that happens, if one moves into the other, we call that spontaneous because we didn't do anything other than remove the barrier between the two. If the other moves backwards, then, for instance, like if B moves into A, then we say that that process is not spontaneous. So spontaneity is based on direction of the actual reaction. So for instance, we're going to see that if we're trying to make something happen, a spontaneous reaction is one in which you cannot reverse it without putting in energy. So for instance, if we have these eggs and we drop them, the spontaneous process is what happens as they drop and they break and they kind of crack all open. The reverse process of putting the yolks back in the egg and trying to recreate the original egg is going to be not spontaneous, because the amount of energy that we'd have to use to do it is a non-zero number. Let's put it that way. Okay. So when we talk about this in terms of chemical reactions, what we're going to see is that our processes may be spontaneous at some temperatures and not at others. So temperature is something to consider here. If we think about what happens in the difference between a high temperature and a low temperature environment, in a high temperature environment, we have our molecules moving and interacting and running into each other. In a low temperature environment, they all kind of stop moving. Not necessarily completely stop, but they start slowing down a lot. So the collisions, or the number of collisions between particles, which is what actually causes the things to be created, is actually going to slow down. So that may be a not spontaneous thing. When we talk about a phase change, right? So here we have an example of a phase change. If we're talking about at a temperature above 0 degrees Celsius, it is a normal thing for ice to melt. Makes total sense. If we're below 0 degrees Celsius, getting ice to melt below 0 degrees Celsius is going to require energy. We're going to have to change the temperature. We're going to have to put something in order to get that to occur. However, below 0 degrees, the reverse spontaneous of water becoming ice or liquid becoming solid is going to be spontaneous. So we can actually say that a reaction is spontaneous based on temperature, and that kind of involves our phase changes. Okay. Another thing in this particular chapter is we officially introduced this idea of a reversible process. So if we can reverse a reaction, then we say it is reversible. And a lot of times every reaction is reversible as long as we have enough energy or we're doing the right thing to reverse the process. And in our thermodynamics chapter, we're going to focus on this idea of systems and surroundings. So think of the system as the beaker, and the surroundings is everything outside of the beaker. If the thing is going to give off heat, we will see that heat can be transferred from the system to the surroundings. And if the system or the beaker needs to absorb heat, then it's going to take that heat from its surroundings. So this is just kind of a definition of how our heat is moving in this particular case. And we can see this as we can also look at irreversible processes in this particular chapter as well. So if we cannot undo something, so for instance, the breaking of the egg, we could say that's an irreversible process because we really couldn't undo it. We could try really hard, but how accurate could we be? Think about the difficulty level, things like that. In reality, there are irreversible processes. There are things that cannot be undone. If we perform a reaction and we can't go back to the original reactants, that's considered an irreversible process. Now, most spontaneous processes are going to be referred to as irreversible. Think spontaneity in the terms of combustion. When we talk about, say, gas becoming fuel for our cars, it's a combustion process, which means we're taking two things and we're creating two new ones. And even if we take those two new things and we try our hardest, we put in enough energy, we may not be able to get those original products or those reactants back. Okay, which brings us to this idea of entropy. And this is a big concept in this chapter. Entropy involves the amount of spontaneity in the universe. And so this was all introduced way back in the 19th century. This all comes from a man by the name of Clausius. And we've heard of Clausius before in the Clausius-Claiborne reaction, but we're going to introduce just kind of his particular theories around entropy in the next few slides. So he decided that there's something going on with heat and temperature, and those are somehow interacting with each other. Those are somehow linked together. So depending on the temperature at which something is actually happening and the amount of heat that is being delivered, we can actually figure out this idea of entropy. Now, we're going to use this as just a simple definition for now. Entropy is something that we use to identify how random a system is. So randomness, just how likely is it to occur, what's actually happening. We can think of randomness as movement. That's the most common way for us to think of randomness. And if you look here, it says something about the various modes of motion in molecules. And what that means is just, how do they move? Are they moving really fast? Are they colliding? Are they moving really slow? Are they barely moving at all? And all things like that. So we will look at what we call the entropy of a system. And entropy is going to be defined by this S value. And just like heat, in the delta H equations, we're going to see that we're going to know what the overall entropy of a system is by taking the final entropy minus the initial entropy. So total energy and entropy are all kind of coming together in this particular chapter. So kind of keep in mind that what we're aiming for is the ability to link E, H, and S. We're going to get there today. We're not going to get there today. We're going to get there this chapter. So entropy itself is going to actually be defined by the amount of heat if the process were reversible. So heat in the reverse direction divided by the temperature at which this thing is taking place. Temperature is always in Kelvin. Q reversible is going to be only available if the process is reversible. Right? So keep in mind, you have to have a reaction that is reversible in order to do that particular math. Which brings us to the second law of thermodynamics. So our second law of thermodynamics is going to involve entropy in general. So the first law of thermodynamics involves heat and says energy can't be created or destroyed. And we purely look at that from an H perspective. We don't look at that from an S or a Q or, we don't look at that from an S or a G or any of those other things. We look at that from a heat or a Q perspective. The second law is going to focus on S. So it's going to focus on the entropy of the universe. So what this second law of thermodynamics states is that the entropy, so the amount of randomness in the universe, is going to increase for spontaneous processes. So this does not say, and I want to point this out, this does not say that entropy is constant. In fact, the entropy of the universe won't change for reversible processes, but since it does increase for the spontaneous processes, this means entropy of the universe is increasing. Kind of cool stuff. And this actually has huge applications in physics and advanced astrophysics and things like that, because what this is saying is, well, if entropy is increasing, that means things are still moving and things are still happening, and everything that started way back when is also now still happening, and it's expanding, and all of those lovely things. So when we talk about the delta S of the universe, so we're talking the overall universe, if we're looking at reversible processes, so processes that are not spontaneous, not spontaneous. Our reversible processes are ones that we can take reactants and create products, and then take those products and create reactants if we put an energy. If we add the total entropy of the system to the total entropy of the surroundings, we're going to get a total of 0 change in randomness. It balances itself out. But for an irreversible spontaneous process, so think like combustion, the total entropy of the universe, which is still going to be a combination of the system and the surroundings, is going to be a big number, built above 0, if you will, a non-zero number, which means if we add the only two kinds of processes we know about, reversible and irreversible processes, the overall entropy of the universe is going to be greater than 0, which means it's always going up. So the amount of randomness occurring in our whole universe constantly increasing. That's the big takeaway, the second law of thermodynamics. So this is kind of the huge summary of the second law of thermodynamics. It means delta S will either come out to be 0 or it will come out to be a positive number, kind of depending on what you're looking at. From there, we can talk about this on the molecular scale, right? The universal scale is awesome, and it's a great thing to kind of introduce to you, but it is not the end-all be-all. We don't really care that much about that in chemistry. In chemistry, we want to know what's happening to the molecules, right? So we're going to move towards the molecular level. So this gentleman, Boltzmann, and we've seen Boltzmann before too with the Boltzmann distribution, has had this whole postulate of how is this manipulating molecules. And so his idea was that since we know that temperature is a measure of average kinetic energy, right? We know that if a molecule is moving really fast, it has a lot of kinetic energy. If a molecule is moving really slow, it has only a little bit of kinetic energy. That temperature is going to be the thing that we can use to actually measure that. Really useful. And molecules themselves exhibit a bunch of different types of motion. And we've talked a little bit about types of motion, but this is a little bit of a different take. So we have 3 specific types of motion for our molecules. The very first one is translational, and that's the one we've focused on in the past when we talk about collisional theory or collision of gas molecules, or the theory behind what happens when 2 molecules interact and change shape and then kind of leave one part behind so it creates a new substance, aka the chemical bond. So translational motion is going to involve the movement of the whole molecule. That means the molecule was in, say, one place and now has moved itself completely to a new place. Vibrational motion is going to be what happens to the atoms within a molecule. So if we look at something like this water molecule and we have the center axis by itself, then the things around it can actually move slightly. They can vibrate back and forth, like you see in this diagram. So you can see them like stretching, right? Over here, we can see them actually vibrating towards each other and away from each other. And the last one is kind of vibrating outward, right? So they can move back and forth towards each other. They can kind of completely like go wonky. Over here, we have the one where they're kind of like boop, 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 boop. Good times. The very last one's going to be rotational. So the molecule itself doesn't like move, like the center of the axes of the molecule does not move, but the outer molecules, it's, you know, it's not center molecule, can actually rotate around it. It's a rotation. And that being said, rotation really only happens around sigma bonds. So kind of keep that in mind. Sigma meaning single, remember. So Boltzmann actually took these different types of motion, and he said that these different ones can actually happen at different instants in time. So if we were looking at a molecule at one instant in time, it may be performing one of these different types of motions at one point in time. And he said that if we did take a little like picture of them at one instant, we would call it a microstate. And that microstate is just going to be like a good snapshot of what might be happening at one point, right? Not going to be an indicator of what's happening all the time, just an indicator of what's happening at one point. And from there, he actually associated a entropy equation that takes into account the Boltzmann constant and the number of microstates associated with one specific molecule. So however many you can measure is going to be however many you can use to determine what the entropy of the system is. Now, in doing this, if he took initial and final processes, right, so he did before the reaction and after the reaction, then he could see what the change in entropy was of the overall reaction. And in doing this, he would see that the entropy increases with the number of microstates. So a larger number of microstates at the end means a larger entropy at the end. What he also then would have seen is that the entropy of a system could be a very, very small number. Now, never zero, keep in mind, never zero, but a very small number either way. So that being said, so if we just kind of think about these microstates, the number of vibrations or translational motions and things like that, if we think about those, this is going to increase if we increase temperature because we're moving the molecule faster, we're moving it more. If we increase the volume, if we increase the number of molecules, we're going to increase the number of microstates. Now, from the beginning to the end of an equation, we're not going to increase necessarily the number of independently moving molecules unless we're breaking them into smaller parts or we're creating new parts from what we started with, right? So if we started with H2O and that's one molecule, it has a certain number of microstates. If we then created H and OH, now we have H, which has its own microstates, and OH, which has its own microstates. So we've created two molecules from one. Right? That's what we mean by the number of independently moving molecules. From there, we can talk about how entropy is impacted by physical state. And by now, I'm hoping you see if we're talking about solid versus liquid versus gas, we should see an increase in entropy from the solid up to the gas phase because our molecules are now moving more randomly. They're moving more in general. They might be more free, right? Like our gas molecules are very free and random versus our liquid molecules, which kind of have to stay together. They slide past each other, but they really have to associate with each other in terms of those intermolecular interactions. And I'm going to actually highly encourage that you examine this table or these diagrams in your book. There is one just like it on page, oh please. This is page 825 in the newer book. I don't know what it is in the older book, but it's in the same chapter in the older book. I think this is section 3 that we're in. Yeah, so this is in section 3, and this is that diagram in that table. The diagram in that chapter. So what I do want you to point out is, or what I want you to examine is, what are the types of motion available in each one, and are they increasing in reality? Is there really a difference between a liquid and a solid? Or I'm sorry, and a liquid and a gas when it comes to the number of microstates of movement? And from there, when we talk about solutions, what we're doing is we're taking a solution, or we're taking a solid and dissolving it into a solvent. So we're changing that solid from its rigid form to maybe a more liquid form. So we kind of think of this as, it's not really a phase change, it's just kind of a solvation thing. But really what we've done is we've taken individual things from our solid and we've surrounded them by liquid particles, which makes them more fluid. And so if they're more fluid, they obviously have more motion to them than if they were in the solid phase. So they become more entropy, so more randomness, right? We're thinking about this in terms of randomness, and a really good way to think of randomness is motion-based randomness. So if it's going to start moving more than it was before, it's going to be more random. Okay. From there, we're going to talk a little bit about entropy changes. So entropy is going to change when certain things occur. Entropy is going to increase when, for instance, gases are formed in general. So when we go from one phase to a gas, we're going to have more entropy. When liquids are formed from solids, so when a solid moves to a liquid, there is more entropy. When the number of molecules increases, more entropy because more collisions, because more movement. The number of moles increases, same idea as the number of gas molecules. More collisions, more movement, more random. That brings us to our last law of thermodynamics, and it just says that the entropy of anything at absolute zero would be zero. Now, we have gotten very close to absolute zero, very, very close, like 0.15 Kelvin away from absolute zero. And this holds up so far, but we don't really want to get there because we don't want molecules to stop moving. Molecules stopping moving is a bad idea. We want there to be randomness in our universe. We want there to be energy in our universe, and taking energy out and creating something that has no energy is kind of scary. It's a little scary. So to my knowledge, we still have not gotten down to an absolute 0 point in our on our planet anywhere, but that could have changed in the last year. So that being said, just remember that when we talk about randomness, motion would stop at absolute zero. If motion stops at absolute zero, it makes sense that there would be no entropy. From there, we are going to talk a little bit about how to do... All right, hi everybody, we're back. So this last section of slides is going to go over standard entropies and how to use entropy values. And so one of the things that we want to look at first is just this table on the right. So there's a couple of different trends that we can observe. The very first one is going to be that the entropies tend to increase with increasing molar mass. So if we just look at this first section, as the molar mass of these things goes up, so does the entropy of those, so does the entropy values. And these are all going to be entropy values measured in their standard states. So what state they'd be in at 298 Kelvin. So let's say we put some H2 together, and at 298 Kelvin, we saw that it was a gas. So all of these are gases at 298, which means that these are the entropy values that we have measured. Down here, we go from H2O up to C6H6 in the liquid form. So this is going to actually be also increasing. So you see this trend for the most part with all of the values that we see. As the molar mass of it goes up, so does the amount of entropy it has. The next thing that we're going to see is that our larger molecules are going to have higher entropies. So the more parts of the molecule there tend to be, the higher the entropy tends to be. For entropy changes in a reaction, we can actually measure that by taking the total of the entropy, standard entropies, which just means whatever they are at that certain temperature. We can take the products and we can subtract the reactants. We've done this particular thing before with our delta H's, same just with delta S values. So again, you'd need values from the tables in the back of the book, in the appendix, and you would need to use those to actually calculate what you've got. Remember that N and M are going to be the coefficients in a balanced chemical equation for when you want to calculate this. And you would do the sum of all the products times their coefficients minus the sum of all the reactants times their coefficients. Exact same process is what we used to do with delta H. And if we want to look at what's happening with our system and surroundings, we know, for instance, that the delta S value is going to have something to do with the heat released from the system and the temperature at which it's actually being performed. So if we're at a constant pressure, which is pretty standard, Q is just going to be delta H. Okay, so this delta S of surroundings becomes negative delta H over T. And then just to kind of remind you that delta S of the universe has to be, for a spontaneous process, greater than 0, and that delta S of the universe is just going to be our system plus our surroundings. So we've defined that at this point. All right, so from here we're going to do a little bit of fancy manipulation, and we're just going to look at what they're doing. So for instance, we took this delta S of the universe, we said that we know it's delta S of the system, and that if we wanted to, we could add that. Remember, we had that negative Q system over T, and we said Q system could also be delta H of the system. We can replace that delta H, or that Q of the system with the delta H. So what we're doing is we're doing a derivation. We've seen them before. We're just watching what's happening. Don't freak out about being able to do this yourself. Remember that our goal is to get to a final equation. And what your book likes to do is actually show you how to get to that final equation. And so this derivation is actually not in your book. It's only in the lecture. Your book is really good at just saying, okay, here are the equations you need to see. And there is a good example of the ammonia synthesis reaction on page 831 if you want to see how they're actually using that delta H to find the delta S of the system, or the delta S of the universe. And so a few things have to be done in order to get this equation to become this. Really, all we did is we multiplied by negative t to get rid of the negative sign and to get rid of t on the bottom of a fraction, and this is what we get when we do it. From there, we're just going to take this negative t delta S of the universe, and we're going to actually introduce Gibbs free energy. And this is actually section 5, so we are done for this particular chapter.